that we could totally do without calculus. And we're going to do using calculus, and you're going to be like, why would you do calculus to do that? We could just use geometry. And you're absolutely right. But if we do it with calculus, you'll actually see that it's the same as using geometry, and then we'll get to problems that might be a little more difficult that you can't use geometry with. So, let's see. Nope. There we go. All right. So, we want to find the volume of the cylinder. All right. So, cylinder is, just out of curiosity from geometry,
Circle, pi squared h.
pi r squared h. Perfect. All right. Now, this cylinder is interesting the way it's rotated, with the way it's built. Normally, you just think about, hey, give me a base and give me a height, and there's your cylinder. We're going to do this a little differently, and it's going to allow us to generate many more interesting volumes than just cylinders. So for those of you who are geometrically inclined, you'll actually be able to see and visualize this. For those of you not, I have someone far more brilliant than I came up with a way of using Sketchpad to demonstrate how these volumes are constructed. So we just started off finding areas, and now we're going to extend it to doing volumes, three-dimensional things. And the definite interval is going to be good for that too. Just like the baby, like slicing up the baby and adding those together, we're going to do that with cylinders. Not really slicing it, my goodness. All right, cylinder generated by rotating the region bounded by the line y equals 3 and the x-axis on this interval about the x-axis. All right, so what in the world are they saying? I have no idea. So we need a region bounded by y equals 3 and the x-axis. All right, so if I do y equals 3, horizontal line, and the x-axis on the interval from 0 to 1, 2, 3, 4, 5. So I'm going to take this region, the blue, and it says rotate that around the x-axis. So I have to rotate it, and that's not a G, that's actually an arrow showing you that I'm spinning. I'm going to rotate it around the x-axis. Now here's the thing. It's not a two-dimensional thing anymore. If I rotate it around the x-axis, Gesundheit, it's actually going to come out at you.
Wait, how does that?
It's coming out toward you, and then it's going to go back behind the board and come around.
So, can we pretend that that's sliced in the middle when it's turning, or are we supposed to think that that's the entire cylinder? Just fanning out.
So actually, what you're saying is right. This actually represents about half of the cylinder once we construct it. Now, instead of me putting my hand like this and saying it's coming out towards you, I'm going to try to use Sketchpad so you can see exactly what we're talking about. So if I go to Sketchpad, this blue region is the region we're talking about, all right? And I can actually revolve it, and it's going to now try its very best to do a two-dimensional interpretation of a three-dimensional figure. Does that work for some of you?
Yeah.
Okay, a lot better than me putting my hand up and saying, it's coming out towards you, right? What? Sure. Oh, it is going. Okay, but so do you agree that it created a cylinder? Do you see the cylinder? And it's actually a cylinder that's on its side, right? The base. And this middle slice is just really trying to show you if you took a knife and sliced down the middle, you would get something that looked like a circle. Okay. And let's see, we can stop revolving, and you can actually, it says sweep the disc. And you can see what it's really showing you is anywhere you cut on this cylinder, you get the same exact shape, which is a circle, right? Is that okay? And I think it'll maybe even go back to the beginning. It does. I'm going to stop doing that, and I'm going to go back, and let's see. I'm going to say, hey, this rectangle can generate a cylinder. Okay, the rectangle doesn't represent a cylinder, but if you rotate the rectangle, it can generate a cylinder. and we get a cylinder that looks like that. And, every year I try my best, right? When we get to some problems, I'll be like, okay, here it is, you rotate it, and it's going to look something like this. And people are like, wow, you're a really bad drawer. And I try again. All right, and then... all right, so maybe something like that. And then I say, hey, look, you could slice it, and it'll look something like this. Or, back on here, you could slice and it looks something like this. So how does first of all, if we had to just use geometry, you already told me the volume is what? Pi r squared h. So in this case, the radius of this is 3. The diameter is 6. The radius is 3, right? Okay. As a matter of fact, the radius is actually, what value of the function is the radius? It's all right, so you could be right. I mean, it's the height of the rectangle, but I was actually looking for the pre-calc answer, which was, it's the y value. That's how tall it is. It's the y value. All right, and then, let's see, so that's 9, and then the height is 5, so we're looking for like 45 pi somewhere down the road. So how can calculus do this? Calculus can do it, and you're going to say, well, why would you do calculus if you can just do that? I understand. So if you actually think about this as a really, really thin slice, and we're going to call them a disk, okay? If you think about this disk as being a really, really thin disk, we could actually add up 10 disks or 15 disks, right? I could just draw 15 more disks and stack them along the side, and that would be a cylinder, right? If I made them a little thinner, maybe I'd have to do 50 of them. It is. It's the analogy is, so this would be like spinning a really thin rectangle, and the analogy is like we did rectangles and we did more and more and more, and they got thinner and thinner and thinner, and they got to be the area. So I'm going to break this down into calculus. We're going to add up lots of little disks. Well, I shouldn't say little, lots of thin disks. Okay? And what's good at adding up thin disks? The definite integral. So, what were you going to say? Oh, yeah, that too, I guess. Each disk has a very, very thin width. And that width is actually along the x-axis. What should we call a really thin width along the x-axis?
Zero.
It's getting close to 0, but it's not.
X.
All right. If we go back to our area example, when we were just finding areas and we did rectangles, we said the height of the rectangle was y, and the little tiny width of the rectangle?
A.
No. Yeah, you're making me sad. It's all right. Dx is the really tiny width, right? So that's when we did, like, height dx. The dx stood for the little tiny width. So are you right if I call the width of that dx again? Okay. So pi r squared dx. And where am I stacking these cylinders to and from along the x-axis? 0, 1, 2, 3, I think 5. 0 to 5. So this is the calculus way of saying, hey, from 0 to 5 on the x-axis, add up all these disks that have a volume of pi r squared dx, where dx is a really, really tiny sliver. Now this is great, except for the fact...
What?
Come on, what's bad about this?
Zero.
I love 0. There's no x. Like,
Isn't that what dx is? Like,
no, but,
it has to correspond.
right, it's r and dx, and r is not a constant, r is a variable, and so I need these to somehow be the same. So, that's okay, because we actually know, in this case, exactly what the radius is. The radius is equal to some y value, which in this case is equal to 3. So I can just put in 9 pi dx. All right, the antiderivative of 9 pi with respect to x? 9 pi x. Evaluate between 0 and 5. Hey, do you want me to? No, never mind. Plug in 5 and you get 45 pi. Plug in 0, you get... Hey, what do you know? That's what we're supposed to get. All right, so good place to stop and pause, ask questions. Would we ever find the volume of a cylinder using calculus? Probably not. It's probably too much trouble than it's worth. But we can find more interesting volumes down the road if we get the strategy down. You want to ask a question? Dan, you're thinking? Mm-hmm. We should do another. Let's do another. All right. We're going to find the volume of a cone. Now, for those of you from geometry, you're going to tell me the volume of a cone.
1/3 pi.
Perfect. It's just 1/3 of the volume of a cylinder. So from geometry, you're going to be like, why in the world would I do it? I'm using calculus. It's okay. Just one more just to, make sure we're doing all right. All right. Generated by rotating the region bounded by the line y equals 2 minus x, the x-axis, and the y-axis, and rotated around the y-axis this time. Oh my gosh, I don't even know what they're saying. This is crazy, I tell you. All right, let's draw a picture. All right, the line 2 minus x has 2 and a slope of -1. Is that all right? All right, so we're going to take this region. All right, between the x-axis, the y-axis, and that, so we're actually taking this triangle, right? And it says rotated around the y-axis. That's gonna... You guys are making me sad again. So it is. It's going to flip over into the second quadrant. And you can actually see its reflection is going to look something like this. And that would actually be, if we slice the cone right down the middle, that's what we would see. I'm going to try my best to do the picture, and then maybe I'll go back to Sketchpad to see if I don't know if Sketchpad will do the... Hold on, let me just see. No, I think I'm stuck. I'm stuck only going around the x-axis in Sketchpad. Sorry. All right, so that's actually a great idea. Hold on. All right, hold on. So if I did 2 minus x. Whoa, check that out. Let's reset this. And I don't want to go to there. I just want to go to here. But it would be nice to make this a little bigger. Oh, I don't know how to make it bigger. Come on, why can't I make it bigger? Oh, that's not what I wanted to do. Sorry. I apologize.
That works.
Yeah, I know. I just wanted it bigger, but that's fine. So it will, but watch. Okay, let's see what I'm going to revolve, and then okay, and then I'm going to stop it, and then I'm going to flip the screen. So there it is, right? That's what we're looking at. That's the cone. All right. All right. Now I have no idea where. Okay. Oh. So let's see. Get well, Ian and Katie, right? Hi to Drew. And Rachel came, right? So we're good. All right. All right. So So you get something that looks like that. There's the axis, and it, I guess, pokes through the bottom there. And so this time, if you slice it along the x-axis, you get like a weird shape. You get something that looks like that, right? That's actually not helpful in this case. If we slice it this way, we get, every time we slice it, we get a little disc. And if you slice down here, you get a bigger disc, right? All right. So that's actually would be a really helpful way to slice it. If I slice, instead of slicing it vertically, if I slice horizontally, so this changes a few things. As a matter of fact, it changes the width of this disc. What's the width of this disc now?
dy.
It's a dy. It's a little change in y. It's a teeny tiny change in y. So what I want to do is I want to add up all the discs, which are pi r squared dy. Oh, yeah, you're totally right. Sorry. 1/3 pi r squared. Well, actually, the height of each little disc is dy. dy is the height, right? That's where that comes from. All right. Let's see. Where am I stacking? This time, instead of stacking along the x-axis, I'm stacking along the y-axis. So I'm stacking them up like this. So along the y-axis, I'm stacking from where to where? Is that okay? From 0 up to 2. I want to add up all the discs that I can stack from 0 to 2. Now look, if you actually messed up, you were going to be right if you said 0 to 2 along the x-axis too. As a matter of fact, does it matter which way I spin this around the y or x-axis? Do I get the same volume? Yeah, I'm pretty sure, yeah. No, it definitely won't. So this is nice. Let's take advantage of it. What happens? Yeah, we could have messed up and it would work. Great. Some people like taking the 1/3 pi and just bringing it out in front. You don't have to. All right. Now the question is, this is r, right? Does r stay the same no matter what disk you do? No. What kind of value is r? It is a changing one. It is a variable, but it's actually the same as one of the other variables that I deal with. Nope. Definitely. It's an x value. Anything that I measure horizontally from the y-axis, that's an x value. Anything I measure above the x-axis is a y value. So in this case, r is equal to my x value. So if I do x squared dy, well, that's not a help, is it? No, but do I know something about y and x? Do I have a relationship between the two? Y equals 2 minus x, which means x is equal to 2 minus y or y minus 2?
You add x to the other side to y.
Okay. If I add x to the other side and then subtract 2 minus y, right? Add x to both sides, subtract y from both sides. X equals 2 minus y. So look, I can do 2 minus y squared dy. And now I have something, I have a definite integral that I can evaluate. Okay? Now, if you're going to evaluate this definite integral, you can either think about the chain and antidifferentiate 2 minus y, or if you like algebra, some algebra, you can actually factor that out, right? You can do 2 minus y quantity squared and factor it and do 3 terms. I'm actually not going to do it. You can at some point, but right now the hardest part is just setting this up. Okay? And we're actually going to get to the point where the setup is going to be as important or probably even more important than actually getting the answer. Right? Because showing that you can set it up is the hard part.
It's also how you get the answer.
Yeah, no, I totally agree. I mean, you can't get the answer without the setup, and the answer is important, but setting it up is important too. Do you want to ask a question? Because I got one more to do. I don't. I've actually been thinking about that. It hasn't been one in a while, right?
They had one
Yeah, I'm a little nervous.
I feel like
I
there's
wonder-
gonna be one
I-
today.
Yeah, go
Why
ahead.
couldn't you just split up the triangles and then set it all around? One question.
So, are you saying cutting it?
Yes.
When I slice it, it actually, I'm not going to get triangles. Are you talking about if I slice it along the x-axis?
It's like a half of a triangle.
No, I'm going to get something that looks like this.
No, not like that. Just exactly like the triangle we have up there, and then just rotate it around.
No, so listen, if I slice down the middle, I will get this triangle.
Yeah.
But anywhere else I slice, I'm going to get a sort of strange shape. So look, if I slice here at this point, I agree that I get a triangle. But right in front of it, there's this curve. So I don't always get the same shape, and it's a weird shape. So if I
Why
slice...
would like a quarter of a triangle and then setting it around and just... Cause like the triangle you have there is
Yep.
set around in a circumference of 2 pi r. So why couldn't you just use that as your...
So you want to take a whole bunch of triangles, little thin triangles,
Why would
and
you
then
wondering if it's possible?
and then fan them out
Yeah.
like. So here's the thing. This, I'll tell you what would be easy if we were doing this in polar coordinates, because we could easily talk about how to spin this. But the problem here is with these triangles, adding them up, it becomes hard to figure out what I'm adding them to and from. Am I adding them from 2 to 2? Right? I'm actually spinning them. So if I think about polar coordinates, I could say, okay, I'm adding from 0 to 2 pi, right? Because that's the circumference of the circle. But I think if I told you that we're going to do polar coordinates right now, you might freak out. Like if I told you in a couple weeks, you might be, all right, fine, I could do it now. Is that all right?
Yeah.
David?
Have you ever had fire go off during screen time?
I don't know. I can't recall. I don't think so, but it feels like we must have, right? I don't know. All right. Different shape. A parabola. So y minus x squared. Y minus x squared is opening down with intercepts at plus or minus 2. This says just the first quadrant part. So I'm just going to do 2 and 1, 2, 3, 4. So it's going to look something like this. So I have to take that shape. And it says rotate about the y-axis to form a paraboloid. Okay, so let's see. I'm going to rotate around the y-axis, and half a sphere,
Half an oval sphere.
half an egg,
Yeah.
a bowl that we filled with concrete.
Or salad.
No, I don't think so. This is, I see it as being
Salad.
okay. A Jello mold. Without the fancy ridges, though.
I know.
Okay.
They cause a little bit of trouble.
That'd be a lot of Jello.
So I'll take like half an egg. I'll take a Jello mold. If we slice it, now here's the trick. If we spin around the y-axis, then the best thing to do is to slice perpendicular to that. If we spin around the x-axis, the best thing to do is slice perpendicular to that. So if we spin around the y-axis, if we slice perpendicular to the y-axis, we get lots of little discs. And not only that, another clue is that when you spin around the y-axis, the width is going to be dy. I'm sorry, I totally messed up. I apologize. Sorry, I promise I'll go back to the problem we just did. This is really bad. So, look, the volume for a cone is 1/3 pi r squared h. That's totally true. But when we're doing the calculus here, we don't need the third. We don't need the third. Because what are we adding up? Are we adding up cones? No, we're adding up discs. Yeah. Every time we're adding up these little circles. Right? So I totally apologize. I got caught up in the geometry, the 1/3, and that's how you do it using geometry. With calculus, all we're adding up are the discs. You're just adding up circles. And the 1/3 takes care of itself because the radius is changing, right? The radius is always changing, and that's taken care of right here. As a matter of fact, if we took the antiderivative here, can you see you'd get a 1/3 something cubed? Like, the 1/3 actually somehow gets involved in the game. Gesundheit. So I totally apologize. That's better. I feel bad because I messed up at the very beginning of learning a new concept. Do you want to ask a question about that?
So the function you use when you're doing this is just always going to be the circle.
Yep.
It doesn't have anything to do with whatever shape you're using.
No, right? So we did a cylinder and we sliced it into circles. We're doing a cone, we sliced it into circles. We're doing a weird paraboloid, we're slicing it into circles. So because I'm just about to say, look, it's dy and it's always going to be pi r squared, right? And then I was thinking, well, that's not what I just did. I did the 1/3. That was wrong. So I want to go back and say, look, it's pi r squared. And that's the beauty of using calculus for these volumes is all we have to worry about is pi r squared. And like I said, some students actually like putting the pi out in the front. Just get it out of the way. You can put it wherever you want. All right, so as soon as I know that it's going around the y-axis, I can think dy. And as soon as I think dy, I can think, okay, I'm going to add the circles or the disks up along the y-axis. So where am I stacking along the y-axis? 0 to 4. And now the only thing I have to contend with is r squared. Well, each radius of this, is it an x value or a y value? It's an x value. So really, pi from 0 to 4 of x squared dy. But that's a bummer. I don't want an x squared and a dy. I need to figure out what the relationship between x and y is. I have it, right? I know. Y is equal to 4 minus x squared. Oh, let's see. You know what I'm just going to do? X squared equals 4 minus y instead of taking the square root. Because what do I need? I need x squared. So pi from 0 to 4 of 4 minus y dy. And I'll do this one because it's simple. 4y minus 1/2 y squared, evaluated from 0 to 4. When I plug 4 in, I get 16 minus 8. When I plug 0 in, I get 0, so my answer is 8 pi. And so here's the thing. The cylinder and the cone, we could have used geometry. I don't think any of us learned in geometry class how to find the volume of a half a paraboloid. Did anyone do that? No. So here calculus is great. It finds the the volume of a very odd shape. And all it is based on those disks. We're just slicing it into disks. Do you want to ask a question? Okay.
How did you know that?
So I saw that I could have done x equals root 4 minus y, but I knew that I was doing pi r squared, and my question was, is r r is an x value. So r squared is the same as x squared. So I apologize. Really what I should have said is like r is equal to x. R is an x value, and then plugged it in. I should have done like an extra step there. Okay. Alicia? Okay. Try something else? No. All right. So here's the thing with the volumes. Today we're just going to focus on pi r squared, and then here are the keys. You have to decide, is it a dx or a dy? And once you know whether it's a dx or dy, you need to figure out where you're stacking to and from A to B. Is it along the x-axis or the y-axis? Then the question you ask yourself is, r squared, is r a y value or an x value? Whoops, holy cow. And then once you figure out if r is an x or y value, you may very well have to use a secondary equation. So if you know that r is an x value, you might have to figure out what x is in terms of y. right? And then once you get the setup, that's actually like half the battle, maybe 2/3 of the battle. After you get it all set up, it's actually, because you're all qualified into differentiators, a piece of cake, either by hand sometimes or, your calculator sometimes, right? So I'd say really the focus is going to be doing the setup. And can I actually see that for a second? So let's see, set up and evaluate, set up and evaluate. So these are all right, set up and find. All right, that's fine. And for the first 6, I actually gave you the regions that you're going to be rotating. So for those of you who are visual people, right, it'll help you think about what it looks like. For those of you who are not, I'd say try your best, to draw the shape, to get an idea, because drawing the shape oftentimes answers the question, dx's or dy's, y value or x value. But like I said, if you're spinning around the y-axis, it's going to be dy. If you're spinning around the x-axis, it's going to be dx. And a lot of things, once you figure out if it's dx or dy, follow from that. All right. A little bit about 10. Kelly, you want to...
I just made it good. I just guessed from the
Oh, Kelly. All right. So it starts with y equals 4, right? And what was the area of the whole thing?
72.
72. So we actually...
No.
Oh.
It was 10 to 10
Was the whole entire thing?
Yeah.
Okay, so I would actually say we can cut this problem in half by saying, okay, we know the area here is 5 1/3, right? And so we want half of 5 1/3, which is 2 2/3. Is that right?
Yeah.
All right. You love fractions, is that what you're saying? All right, so we need a line somewhere here that's y equals c. All right, so tell me this. What'd you guess? How'd you start guessing in...
Well, I did 2 since it was half of 4.
Okay, and that didn't work, right?
No, but
Okay.
then I just started moving it up like 2.1, 2.2.
Okay.
And then I got to 2.5 and it was half of the...
All right, so you actually have to move this up a little bit more than halfway, right?
Yeah.
All right, David?
Could you just put undefined, since it was split it in half, just right down the middle, where it's technically not line?
No.
Say that again? I don't think so, but say it again.
If you go up to the top one where it's the actual full plan,
Uh-huh.
the line straight down the middle is actually splits it.
No, but we're doing the line not down the middle, straight across the middle.
Okay.
All right, so we're trying to find this half such that it's equal to this half. And I would actually say then we know what the blue has to be. We're looking for the blue value to be 2 2/3. So Kelly's saying, look, you can actually just keep moving up the C value and doing some guessing and checking. I think we could actually set something up.
Could you set up 2 instead equals
Okay.
something? That's how it's a little between 0 and 2.
All right, so this is a good start. Between 0 and, well, this 2's out here. So the question is, what value is this 2 along the x-axis? What value is this point? Like if we're going to add up areas, right, from 0 to what? Now 0 to 2 takes us all the way out to here. This point is 2, 4. What's this point? That's a hard question.
C squared.
You are on the very, very right track. If the equation is y equals x squared, and we know y equals c, I'm telling you the y coordinate is c.
X squared minus 2.
Root C.
Root c. This point has to fit the relation y equals x squared. I know y equals c. That's what we're saying. On this line, y equals c. So what's the x value have to be? It has to be the square root of whatever y is, right? This leads us to the conclusion that x equals root y. So, I don't know. From 0 to root c, aren't we just doing the tall minus the small? What's the tall function?
Y equals 4.
Nope.
No, no.
Y equals c. And what's the small function?
X squared.
X squared. I think you could do that now. So, I'll leave it at that. Kelly sort of gets us started. Alicia gives us a way of setting it up with calculus. Yeah, nice work. Oh, it's